In this example, one of the 4 benchmark problems presented in MacDonald et al. Is analyzed to test the 1D channel flow model in IGW. We model a 1 kilometer long trapezoidal channel with a bottom width of 10 meters, a 1-to-1 side slope, and a discharge of 20 cubic meters per second. The flow is subcritical at inflow and experiences a hydraulic jump at 2/3 the distance along the channel, and then remains and is subcritical at the outflow with a depth of 1.35 meters. The Manning roughness coefficient is 0.02, and the bed slope is shown in the figure. The analytical solution for this test case for steady-state flow is available for comparison. Open IGW from the desktop. The GIS Google Map interface will appear. We can also switch to the GIS Layer Explorer to input GIS layers. Close this and observe the IGW interface in Workspace. We need to set the extent of the workspace, change the units to meters, and enter a 1000 meter by 100 meter modeling workspace. Next, go to Display Options and remove both the horizontal and vertical scale bars. Then, click on the Create Polygon icon to create the domain polygon using the Input Vertex Coordinates input box at the bottom of the workspace. Each pair of XY coordinates must be followed with an Enter keystroke, and the text box must be cleared before entering the next set of vertex coordinates. The end following the last coordinate pair closes the polygon by connecting a line between the last and first vertex coordinates. Next, we need to create the channel by using the Create Polylines icon and double-clicking on the Input Vertex Coordinates box at the bottom of the workspace. Create the channel link from the channel configuration file. Edit this link by selecting the link and bringing up the Attributes Explorer window. Then select Two-Way in the Head-Dependent Flux box and click the ... icon to open up the Polyline attribute table. In the Node Type column, or End Type, change the node type of the first node from 1 to 2 and hit Enter to bring up the QH window. Click Edit to assign the boundary conditions to this node. In this example, we will use a constant flow boundary condition. Please make sure to use the correct units when entering the flow rate. When you're finished, click Save Edit and then click OK. The last node of this channel is assumed to be the exit node. Change its node type from 1 to 999. The channel depth is assumed to be 1.2 along the entire channel. Change all of the values. Then, the channel cross-section in this example is a trapezoidal shape and the channel slope is variable. Go to the cross-section file load icon and load the cross-section. The first line is the total number of cross-sections. Then, for each cross-section, we use a line to state the relative location of the cross-section, the number of vertex, followed by a 0. And then the line below, the coordinates and roughness of the first vertex, the second vertex below that, and so on. In Attribute Explorer, click Layer 1 and the Surface Water Channel button to bring up the Surface Water More Options window, and turn on the Channel Flow module. Click on the clock icon to set up a transient model. The global time step used in this example is 6 seconds, which means the channel flow time step is 0.1 second. Next, discretize the model. A surface water monitoring well will be automatically created at the last node. Open this monitoring well window and customize its size. Click On/Off Channel Cross-Section in the button panel at the bottom of IGW and move the cursor along the channel to view the cross-section at each node. In this cross-section form, link and node information and water depth and water level at the current time step are shown at the top of the chart. Run the model and select a parameter to show in the Monitoring Well window. IGW allows the user to stop a transient model at any time to customize the display of the results and charts, or to dynamically draw a profile. In this example, the steady-state solution is simulated using a transient model. When the outflow rate reaches a steady-state value, the model results can be treated as a steady-state solution. Then, we can stop the model and export the results for comparison.